Hello. Today we'll move to BGW, multi-party computation. So a different idea for how to arrange secure computation altogether, although it will be similar in some ways to GMW. Because it's based on secret sharing, but it's a different form of secret sharing, a more general one. So let's introduce this first. Okay. So today we'll show the BGW, I think it's 88, multi-party computation. And the difference is that this is for a general threshold setting. Actually, no, for a honest majority. So such that n is greater than that t is smaller than half of n. Okay, and compare to GMW where t was n-1. And okay, so the BGW computation is also the target computation model is arithmetic circuit. Arithmetic circuit over some field. Okay, so you have operation plus and product in the field, and your gates are either additions or multiplications instead of Boolean gates. Okay, so in the case of GMW and Yao, we had Boolean circuits. Okay, and at first, as usual, we'll do HPC model of attackers. So the threshold of faulty players in the system will follow the protocol, but we'll just be concerned with what they get from the view of the computation that they get in the MPC protocol. That this could be emulated given just their inputs and outputs, right, as in the MPC definition. But upgrade to active attackers, which we spent some time last time, right, using zero knowledge proofs for well, either Yao or GMW, uses well, it can be done because this was a general compiler that if you have an HPC protocol, you can, what do? You do a coin toss to create randomness for all parties, and then you run zero knowledge proofs at every round. We did this in the case of two-party computation, but it generalizes to a multi-party setting. But here there will be a native procedure used for active attackers via something called verifiable secret sharing. Okay, and right here, I realized that I have not said that the basic tool in a GMW computation is a secret sharing scheme. by Shamir. Okay. I guess maybe it can be generalized to other forms of secret sharing, but it's in its basic form, it targets this secret sharing scheme, Shamir Secret Sharing. Okay, so that's another thing of these MPC protocols, right? Like with GMW, you saw the beautiful tool of oblivious transfer. With YAO, we added circuit garbling, a sort of amazing procedure, really, that you can do. And here there will be likewise a very powerful tool of secret sharing that is not just used here, but finds uses all over the place. Okay, so what is secret sharing? Secret sharing is a two algorithms. Algorithms to deal and algorithms to reconstruct. Okay, with the syntax that the deal, or I guess this one is called share. The share protocol, the share algorithm shares a secret called, actually, let's call the secret S, into shares S1 to Sn. So we'll show the secret sharing for Tn threshold, where n is number of participants, and T is the max number of faulty, meaning corrupt participants. Okay, we'll see what we mean by what kind of faults are we concerned here with. But let's first assume everyone is honest and just see what the syntax of the scheme is. So the picture is that there is some party called a dealer who has a secret S. And what the dealer wants to do is to share the secret among a group of players such that later these players will be able to reconstruct the secret S. This is called the sharing. And this phase is called reconstruction. Okay, and okay, so the share algorithm is a randomized algorithm that creates shares of a given secret, and the reconstruct algorithm takes the vector of shares and typically in a deterministic way reconstruct a secret. Completeness is that the reconstruct algorithm on the output of a share algorithm on S always gives you S, okay, for any run of these algorithms, right? So what if you shared something and then they reconstruct, you get what you started with. Secrecy is the key issue, right? Secrecy is that for every set, let's say, bed of indices from 1 to n, which determine who of these n players are bad, meaning corrupt. But we limit the size of this bed set to be under this threshold T. Okay. And what we want for this is that the distribution of the shares of the bad players, where the vector of shares is created as an output of a share algorithm on some secret S, is indistinguishable or perhaps identical and identically distributed to a set of shares of the same bad players, which result from sharing some other secret S prime. And this has to hold for all S and S prime. And the notation here is that, well, this is the vector S, this is the set of, right, this is the vector of all shares. And SB stands for the set you expect, which is SIs for I in B. Okay, so what this definition says is that if you have, there's two secrets. Think of these as two messages, right? M0 and M1. If you share message M0, you create some vector of shares, and then the bad guys' shares are these. In another scenario, what you shared is some other message M1, and the bad guys got the resulting shares at their indices. And we say that the secret sharing has a secrecy property if basically if what the bad guys get is they cannot tell whether they are in this case or in this case based on their shares. Okay, and typically this is stronger than this is just identical distribution. Okay, so many secret sharing schemes are information theoretic secrets. So the shares that the bad guys get in the two cases are not just indistinguishable, they're actually identically distributed. So you have seen GMW uses XOR sharing. Where the threshold is actually you can get n-1 shares and you still don't know anything. And what's the sharing? The share procedure on secret S picks S1, S n-1 at random in the appropriate size bits, right? Where here the secret is, as I assume, the secret is n bit long. So I pick n-1 shares completely at random and set as the last share to be the secret XOR the XOR between all these shares. Okay, and it's easy to see. Okay, so what is the reconstruction? Well, it's obvious. I take all the shares and XOR them, and I get back S, right? Easy to see that for all B, which are size 1 less than the full set, the vector of shares that are created in this way. So clearly, if B is just these n-1, it's true. Yes, these are just one-time paths. So by definition, they are independent of S. But it's easy to see that, you know, in any other set, if this set includes the last guy, Well, here S was operated, but the set is missing one of these paths. So therefore, it's a one-time pad under a perfectly secret key. Okay, so SB is distributed as n-1 tuple. Oh, sorry, n is both the size of the number of players and the size of the string. Okay, well, I guess I will call this n hat. Okay, the size of the string. n-1 tuple of random n hat bit strings. Okay, so you have seen one secret sharing already, right? And it was used in the GMW protocol. Okay, so let's see Shamir secret sharing, right? Shamir secret sharing works like this. Assume that the secret S is in some field F. Okay, and the share algorithm on S picks random t-degree polynomial f over the field f, but random to the subject to the constraint that its value at 0 is s. Okay, so in other words, f of x is a0 plus a1x plus atx to the t, and all the operations are over this field. So think modular residues mod some prime p. Okay, so just simply all these operations are modulo p for some prime. Okay, so this is the polynomial where subject to constraint that a0 is s, right? Because evaluation of this polynomial at 0, all of these drop out. It's just a0, and it should be s. So the free coefficient is just picked to be the secret, while a1 to at are just chosen at random from the field, right? So this is it's a tuple of t elements in the field. Okay, this vector. Okay, and then share Si is set to be f at evaluated at point I. In general, we can use other evaluation points. So, in other words, Si can be some evaluation of f at some point alpha I, where there is some correspondence, yes, that takes indices and embeds them in the field. Okay, so and it's important that it's one-to-one, right? So no players are assigned to some points in the field, and the share of that player is the evaluation of the secret sharing polynomial at that field point that is assigned to that player. Everybody knows these points, okay, and they all have to be just unique. For simplicity, we can say that you just evaluate at his index. The more general form, it has to do with efficiency of reconstruction and some other basically secret sharing is also error correcting codes form secret sharing, which basically are Shamir secret sharing procedure. But when these points are chosen appropriately, then you get speedups in evaluation, and also error tolerance to fault, which we didn't speak yet. So far, we're concerned just with secrecy, but another concern of secret sharing will be, what if in the reconstruction, some of these players give out erroneous shares? So not only they try to learn what the secret was, but when there's time for reconstruct, they substitute the true share with some other one. Well, that is exactly the error correcting question, or or close, because often error correcting codes are designed for random faults, and these guys might not act, might not substitute their shares with a random one. They might maliciously choose them, okay? But some error correcting techniques are resilient against arbitrary faults, not just random ones, and it will have to do with the choice of these evaluation indices. Okay. So that's it. Okay, that's how you choose your shares. Now, what about the reconstruct algorithm? So a reconstruct takes all these shares evaluated in this way, right? And what does it do? Pick any t+1 subset of indices. Call it the good set, okay? And right now we are only concerned with HPC faults, so nobody diverges from the protocol, so all those shares are assumed to be correct, okay? So we just pick some t+1 subset of them and interpolate interpolate F, i.e. compute F0 from the set of the values of the polynomial at these in t+1 indices, right? And t+1 t degree polynomial can be reconstructed from meaning interpolated from any t+1 evaluation points, i.e. x, f of x pairs. Okay, so just visually recall, okay, a linear function, right? If I give you, so here the degree is 1 because it's a linear function, and if I give you 2 points of it, right, then you can reconstruct this line. And given any quadratic, if I give you 3 points, that suffices to, although of course visually it's harder to see why 3 points are suffice to reconstruct the quadratic. Okay. So, all right. How does the interpolation work? Okay. So, of course, okay. So this is there's lots of algebra, right? Linear algebra. We can talk about this, but there's lots things to say. But here is a maybe simple linear algebra view of polynomial evaluation. So You can think of polynomial evaluation in this way. So I have a matrix of evaluation matrix, which I apply to the coefficients I have chosen for this. So these coefficients determine polynomial f. Okay, and I want to represent computing shares. So these are my shares I will compute. So this is the vector of shares S, and A0 is the secret S, the secret, and these are the shares, and this is the secret sharing polynomial. Okay, so what's the matrix here? It looks like this, right? I evaluate, so S1 is, so in general, Si is A0 plus I A1 plus I square A2 plus dot dot AT of AT. Sorry. Okay. Sorry. I to the T is the coefficient. Okay. Or it's not a coefficient. Coefficients are the AIs. Okay, so what do these rows look like? Well, for the first guy, so this is the I equal 1 row that corresponds to evaluating the share of the first person, right? So all these would look like this, right? Because powers of 1 are just all 1. The I equal 2 row is 1, 2, 4, right? And the last thing is 2 to the T. And so on and so forth. So in general, they look like this. Okay. So call this matrix M. Okay, and secret sharing is just evaluation of this product. I pick these coefficients at random. A0 is fixed as a secret. There is this fixed matrix. I do the matrix multiplication and I get the shares. Now, how do I go back, interpolate from the shares to the, and in fact, I'm kind of, at this point at least, not interested in reconstructing all these shares. All these coefficients I'm reconstructing. I'm interested in reconstructing the A0 coefficient, which is secret, right? Well, I can, the dimensions of the matrix M, right, is that it's n in this way, in this direction, and it's t plus 1 in this way. Okay. Sorry, it's the other direction. T plus 1 here and n here. Well, think of Mg to be the submatrix of M, where you take rows corresponding to indices in G. Okay, so let's say you take the first T plus 1 players. So this would be this top submatrix, right? Mg. But really, G just tells me which row to take, and I take some T plus 1 rows. So Mg is a matrix T plus 1 by T plus 1. Okay. This is called okay, Van der Mond, but I actually don't know how to spell it. Van der Mond matrix, and it's invertible. it's always invertible. Okay. In fact, it's invertible no matter. So here, for any choice of different indices, right? So if these are not, so here at ith row, and I have I to the j, ith row and jth column. If I took arbitrary evaluation points alpha I, the row here would be alpha I to the j, this value. This would be invertible no matter what alphas you check and what are the alphas that you evaluate this on, as long as they're all different. Because this matrix is invertible, so now this matrix determines the set, the shares that are indexed in the set G. So SG is mg times this A vector. Okay, and therefore it follows that A vector can be reconstructed as an inverse of this matrix time SG, and in particular, this gives you A0. Okay. If you want to, you're not, in this route reconstruction, you're actually not interested in computing all these, right? So as you do this matrix inversion, what you really care about is not all the elements here, but just the row that will allow you to compute A0 as some row, right, applied to S. So this row has a known form. Well, first row of this column, of this matrix, is known as Lagrange coefficients, alpha alpha I, yes, I in G. So it's a vector of t+1 coefficients. It's the first row in the inverse matrix. And what these coefficients give you, right, is that you can reconstruct the secret, which is which is f of 0, which is A0, as a sum of these coefficients applied to the shares for I in the set. Okay, so these are computed, easy to compute, based on just set G. Okay. Okay. So well, we can give the closed form, but it's it's not that complicated. But let's just stop here digging into this and say, well, there is this linear coefficients which allow for this reconstruction, and it just follows from the fact that this a polynomial evaluation matrix, any t+1 submatrix of this is invertible. Okay,
Professor?
so okay. Questions?
Professor?
Oh,
so lambda I will be essentially the same, right? It will just, if we store one of them, we could use permutations to find the other ones very easily.
Wait, lambda i's are the same as what?
So let's say you take another G, since they have the same number of elements, wouldn't it be easy to get the other ones by just applying a permutation somehow?
No. The lambda i's are basically for any for any submatrix G. It's a MG always looks like this. Some share, some evaluation index, the first evaluation index to the 0, to the first, to the t's. Then a second one to the power 0, to the power 2, 1, to the power t. Okay, and then
I see it now.
Plus first one to the power 0, to the power 1, to the power t. The choice of G really is the choice of these things, right? Alpha 1, alpha 2 in this case is some subset of 1 to n. I just choose t plus 1 of these indices, okay? And they determine these. For a different choice of G, this set is different, this matrix is different, the inversion of it is different, and the first row of that inversion is different, okay? They're not permutations of one another.
Right, yeah, the shares are very asymmetric. I thought we had some kind of
the lambdas,
yeah.
Yes. But whatever the lambdas are, they're just defined as the first row of an inverse of this matrix. Okay, and they have a not a hard, a simple closed formula too. Okay.
Right, because you could do the usual Lagrange interpolation for polynomials, right? But I guess we wouldn't have a simple linear.
That is it. That's what
yeah.
I'm talking about. I'm just exactly, that is the Lagrange interpolation. Well, but it is, I think, instructive to see that well, okay, why exactly it always works. Okay.
Okay, thank you.
Okay, now, okay, so secrecy. So this was so far reconstruction, and secrecy, right? So okay, so let's this set of shares is this M matrix times the set of coefficients. Now, I want to change it a little bit, and instead of looking at the whole evaluation matrix, which looks like this, n to the 0, n to the 1, n to the t times a0 and the rest of the vectors of the polynomial coefficients. I want to separate this secret S and just and treat separately the secret and the randomness used in the sharing, because this is the secret that I'm sharing, and this is the randomness of the dealer, of the share algorithm. Okay, so secrecy will work very different, will treat this coefficient very differently. This will be the message that I'm arguing is kept secret by any subset of T of these resulting shares. And this is the randomness, which will work like a one-time pad, hopefully, right? Basically, whatever the adversary gets as just T of these shares is some form of this message being encrypted, okay, by enough of key material to argue that what he gets is independent from this message. So let's split it, but that's easy because A0 always acted with the coefficient 1. Okay, so I can rewrite S using this polynomial evaluation matrix. Basically kick out the first row and just apply it to the reduced coefficients, which are now, this is now all the randomness of share algorithm combined in one vector. And what do I do with A0? I just add it. Okay, so it's like this. Yeah, so every element here, right, is a product of this evaluation plus A0. Okay, so now what I want to claim is that for every A0, for every set of bad players, the bad is, let's say, just the maximum t elements, right? So without loss of generality, we just give t shares to the adversary. And I want to argue that SB, which is, now what is SB? It is, let's call this matrix M prime, and let's call this vector of coefficient A prime. Okay, this is a reduced matrix with the first row kicked out. This is the reduced coefficient vector with the A0 kicked out. So what is SB? Just a subset of these four indices in B, right? So again, this is a set of shares for players in B. Well, that is this reduced matrix, but reduced further to just rows corresponding to B, right? So these are rows in M prime for rows in M prime which are in B. Okay, so what I mean is that you take the index. Let's say B has the first, its indices from 1 to T. No, hold on. Okay, no, I rendered this badly. Okay, sorry. No. Yes, sorry. I kicked out the wrong thing. I shouldn't be kicking out the first row, right? Because the first row is applied to the whole vector, and that's S1. Then this is applied to the whole vector, and this is S2. No. What I'm kicking out is the first column. Okay, right? Look, take this row and multiply it by this thing, right? If I want to kick the A0 out, so the observation is that this stuff is all ones, the first column. So that's what I'm kicking out. Okay, sorry. So this matrix is matrix M prime. Okay, sorry about this. Okay, but now do you see this? Okay, I shouldn't have kicked out the first row. I should have kicked out the first column. Yes, because these are the points of the matrix which will act on A0. Okay, if I put A0 outside, anyway, yeah, Okay, then I have to remove the first column. Okay, so yes, so now think of B having the first T players. So what's M prime B? It's the first T rows of M prime. Yes, that just compute the first T shares in S in the S vector. So this is this matrix multiplied by A by this vector of coefficients plus this A0 vector, right, which is just A0 multiplied what? T times. Okay, so okay, this is a funny notation, but this is stands for this vector T times. Yeah, it's a t-dimensional vector whose entries are all A0. And the claim is so that this SB is okay. So you know what? First, let's just observe. This is what SB is. Okay. And the claim about it is that for any A0, which is equal to the any secret, right? So A0 is fixed as secret S. And any subset of T bet players, the distribution of this SB vectors is identical to T tuple of random field elements. Okay, so this process of computation, where this is a random T tuple of field elements. So from the point of view of bet players, what happened during the sharing is the dealer picked a random T tuple of field elements. These are the random coefficients A1 to AT, and used this public matrix M prime reduced to just rows that corresponds to players in B. Multiplied this random T tuple and added this vector who just has a secret S everywhere. It's actually easy to see that this is equivalent to a one-time pad. In other words, the distribution of these results is independent of this vector A0 of A0s. Because this part acts like a one-time pad. Why? Because this is a okay. So why is this a one-time pad? Because for any set B, the distribution of when I take values like this for a random vector in the field, that is this distributed identically to just a random vector in the field. Okay, so if this was true, if these elements for random choice of coefficients look like a T-tuple or random field elements, then by one-time path property, right? This random T-tuple of field elements masked out these values. So therefore, SBs are independent of, right? They're just a uniform T-tuple of field elements. Okay. Now, why is this true? Okay, and this is that's because M prime B is invertible for every set of okay of T players. So it's invertible, and therefore a function that takes a T-tuple and outputs this T-tuple multiplied by MB prime is a one-to-one function. So therefore, as a linear transformation, right? It takes it's just a permutation on this on a vector space over field of dimension T over field F, right? You take a random vector, and because it's a permutation in Ft, applying the permutation to a random vector gives you a random vector, okay, and therefore a random T-tuple, and therefore it looks like this, and therefore this is a one-time path. So what I want to point out is that the fact that these polynomial evaluation matrices are invertible is used in interpolation and reconstruction, and also is used here to actually argue secrecy. Okay, and you can see both as just implied by linear algebra facts. Okay, so that was Shamir Secret Sharing, and look, this is just to get back some intuition, right? What does it mean for a linear function? So my point at 0 is the secret. Evaluation of the function at point 0 is the secret. The other coefficient is random in the field. So what's the polynomial? Well, secret sharing polynomial f. It's a random line that goes through this point. So if I see a single evaluation point of that random line going through point S, that point is random, and it does not matter where in the field it is, right? As long as it's not 0, where it's fixed, the evaluation at any other point is random. And it's the same for a quadratic. Again, okay, so here, well, yes, so I use the fact that it's a field, so it has to be, during computation of these inverses, I will need to divide, yes? So to compute the inverse of the matrix and to argue that it's invertible and that therefore it's a one-to-one permutation, I need to be able to divide in the field. I mean, I also need to divide to reconstruct, right? Because reconstruction worked through division. And even though I'm interested only in the first row, the Lagrange coefficients have divisions in them. Okay. And why can I divide? Because it's a field, right? So that's why we took modulo prime, so that division of everything is possible, except for a zero element.
Professor.
Do
we need to take AI not zero? I could see that.
No, because basically none of these arguments are concerned with, they all go by this matrix.
Right, because you wrote F+.
The coefficient here is just a linear function of the matrix. So like none of the, the whole thing is about invertibility of this matrix. It's not about where this,
Okay, so we don't need F plus there. I thought that's what you meant.
Oh, no, sorry. So F to the T, meaning
oh, okay.
the T tuple over F.
Oh, all right.
Yes, sorry. Yeah. It's a vector of T tuples over field F. Yeah.
Right.
Okay. So so now that we have this Shamir Secret Sharing, let's go back. Let's go to BGW computation. Okay, so here the circuit is an arithmetic circuit. So the gates are either plus or mult in field F. Okay, and the inputs as right, perhaps they go to different gates. Etc. Okay, and so let's call X all inputs to circuit C. Okay, and this circuit is going to continue, building these using these arithmetic gates. At some point, it had outputs. Okay, and this output is a vector Z, right? And the length don't have to be the same, but let's just use this as a simplifying thing for notation. So these are the outputs of circuit C. And here is your circuit C, right? That has these arithmetic gates, eventually resulting in these outputs. Okay. Now, wires 1 to n are partitioned among, so these are input wires, are partitioned among players, among the players. Okay, sorry. Here, n again is the size of the, I used it for the number of players. So let me write it like this. So the indices of the wires are from 1 to n bar, and the players are from 1 to pn. Okay. So P1 is responsible for some subset of these wires, P2 for some other subset, etc. Right? BGW computation goes in first stages. Stage 1, sharing. Each PI secret shares inputs corresponding to PI's input wires. So there is some subset of wires that are supposed to be P1's inputs. He has some values on these wires. He secret shares them. And P2 does the same with his set of shares, etc. What's the result of this first sharing stage? Is that for every input wire W, players hold a secret sharing of XW, which is some set of shares, S1, I can index them with the W, S2 of W, etc., Sn of W. Okay, these are shares of input on wire W, right? Each of the players for every of his input value perform the secret sharing, and well, think of this as a Shamir secret sharing, right? So these are results of Shamir secret sharings for the corresponding X, input X. So now we have the invariant that on all the input wires we hold secret sharings of them, of those inputs. The computation stage is that for gate by gate, so for every gate G in the circuit, such that shares of input wires to G are held. Okay, so at the beginning, what the players hold is secret shares of some gates, which are the sort of the first row of the circuit. They don't have yet, for example, for this gate, they don't have secret sharing of these inputs. But in whatever order, in the first layer of the circuit, take the gate and apply an MPC protocol corresponding to this gate that takes the secret sharings of XL and a secret sharing of XR and creates secret sharing of the gate applied to XL and XR, where XL and XR are respectively left and right input wire of gate G. Okay, and gate G, there is really two cases of gates. Case one, G is an addition, and case two, G is a mult. So we will just go gate by gate, and there will be for each of these two cases, for the additive gate or a multiplicative gate, we'll have a protocol that gets that all the players perform, such that if they start with a secret sharing of the input to the gate, the left input and the right input, then they end up with a secret sharing of the output Okay, and the output is correct. It's a secret sharing of the value that really is a computation of the appropriate gate operation applied to the secret shared inputs of that gate. And this must be secure computation, meaning that if you take a set of corrupt players, of whom there is only t, so less than a half, and you look at the inputs in this computation and the outputs of the computation, then you can simulate everything else that they see in this subprotocol. What is the inputs and outputs? Is their shares of XL and their shares of XR. The output is their shares of the output wire. But now, if these are secret sharings, then their inputs and their outputs are independent of the actual share, right? That was what we argued for the Shamir secret sharing, that the crucial secrecy property, which is that shares of any set of bad players are independent of the shared value. Okay, which would here mean that whichever subset of these shares the bad guys hold is independent of XL, and likewise here it's independent of XR, and the shares of the output are also independent of the shared value G of XL XR. So the inputs and outputs are independent of anything meaningful. And the MPC property means that whatever happens in the subprotocol is simulatable from these irrelevant inputs and irrelevant outputs. Irrelevant from the point of view of the secrecy, right? Both the inputs and the outputs of the bad guys in this transformation are independent from meaningful stuff, namely secrets shared on those secret sharings. So if we show that there is these sub-procedures, then the bad guys just go from shares to shares, from shares to shares, from shares to shares. They basically don't see anything. And secrecy of the whole computation would follow. Well, and so that's correctness. The final phase, of course, is that once you are done with this gate-by-gate computation, then you reconstruct. So there is a reconstruction final phase for all output wires. For every output wire W, reconstruct XW from its secret sharing, right? And if this protocol, if we have the protocol for each of these gates, which goes from Shamir secret sharing of inputs to Shamir secret sharing of outputs, then the final shares on the output wires are also Shamir secret sharings, so we can reconstruct them. This structure, by the way, is exactly the same structure as in the GMW protocol, right? The sharing was an XOR sharing. The computation was gate by gate. The gates were Boolean gates, so not arithmetic. And the MPC protocol that allowed computation of an arbitrary Boolean gate was based on OT. And reconstruction was a reconstruction of the XOR sharing, right? So it has similar, blueprint, really. Okay. So in some sense, this is not new, right? It's just instantiated with Shamir secret sharing and these arithmetic gates now. So we would be done if we showed the subprotocol for these two gates. Okay, so let's do that. Here's the BGW continued. What we need is the MPC the gate subprotocol for G, which is addition, and G, which is mult in the field. Okay. So here is a nice and easy case. If G is a plus gate, i.e. The output is simply the sum over field F, right? So what this gate does is that it sums the inputs. Then the MPC for this gate is non-interactive. In fact, the protocol is could not be simpler if SS secret sharing for XL is denoted as X1 on this XL, S2 XL, SN XL. So these are the secret shares of XL value, and the secret sharing of the right input, let's denote it as 1 XR, as 2 XR, and SN XR. Then the secret sharing of their sum is just sum of these two shares, S1 XR, S2 XL plus S2 XR, ... And each player does this. In other words, each PI simply simply sets S of the output wire SI to be the sum of his shares corresponding to these input wires. So this is the share of the output wire of gate G, which is a plus. Okay. And of course, all the numerical, all the operations are over field F. So why does it work? Because you know, remember the shares of a secret is you know, no, let's say ith share of the secret of a secret A is evaluation of a polynomial associated with the secret at point I. So this is where Fa is the secret sharing polynomial sharing secret A. The share of value B is the secret sharing polynomial at point where FB is the secret sharing polynomial sharing B. So if I define my share as a sum of these, well, that's an evaluation of a polynomial at I, where F is just the sum of Fa and Fb. How do I sum polynomials? Where I so sum of the polynomials defined as f of x is simply the first polynomial evaluated at x plus second polynomial evaluated at x. Now, it's a t-degree polynomial. Right? Because if you have some t-degree polynomial, two t-degree polynomials, and you define a new one in this form, okay, as adding evaluations of the two, well, that's a t-degree polynomial, right? Because if this is some polynomial t-degree polynomial, and this is a t-degree polynomial, you just add them coefficient-wise, and you get at this polynomial, right? So this corresponds to coefficient-wise addition. This polynomial is defined by coefficients who are index-wise sums of the coefficients of this and the coefficients of this. Okay. So if you add the if you add the shares, you are basically sharing using this new polynomial f, which is the sum of the previous of these two. And note that what's f of 0? Well, that's f a of 0 plus f b of 0, which is a plus b. So in other words, the set of shares created this way is a secret sharing of a plus b. Okay. You can also see it from the matrix from linear algebra, right? Like if this is one set of shares corresponding to it's a fixed matrix, right? This matrix does not change with sharing. So this set of shares is m times the a vector. This set of shares is the same m times the b vector. If I add the two vectors, it is m times a plus b. So that's exactly a plus b is the coefficient that define f. And what's the free coefficient of a plus b? It's the free coefficient of a and the free coefficient of b added, right? So this corresponds to the shares, the secrets shared by the a coefficient, the a secret sharing, and the b secret sharing. Did I lose you, or did I manage to keep you the stuff?
I'm good.
Okay.
I wonder. I guess the multiplication will be harder because the degree will increase.
Yes, exactly.
Okay.
Yeah. Okay. So if this circuit consisted only of addition gates, this whole thing will be very simple. We would share, then we would non-interactively keep on adding proper stuff locally from shares to shares, and then at the end we would reconstruct. we need the mold gate, and you know what? I'm out of time, so let's do it Thursday. Case 2, G is a mold gate. Next time, yes. I keep spilling over time, but there's really no reason to do so. Yeah, so we'll see how to do the mold gate, and also we'll see how to make it secure against malicious parties using the verifiable secret sharing concept. Okay. So if there's no questions, then I'll see you all on Thursday.
I have a question regarding kind of the course structure.
Mm-hmm.
So there will be a homework that we will be doing sometime between now and the end of the quarter, correct?
Oh, okay. Yes. So you're due for a homework. Yes, I'll make it. Later this week.
Sure.
Yeah. So some of the questions were, I think I said like, okay, this would be a good exercise. This will be a good exercise. So I would just write those down, and add to it.
Okay, and there will be some, I imagine, some test, basically the final at the end of the quarter.
No, I will not do that.
Okay, that's fine.
Okay.
Yeah.
All right.
Okay.
Okay. Okay. So I will see you Thursday.
Okay. Thank you.
Bye.
Thank you.